All right. Any questions on the previous chapter? I know y'all already taken the test, but still. Okay. We've got class today and Thursday this week, and then just Tuesday next week. And then the following week, if I get my final approval, we won't have class because I'll be gone that week. But next Thursday and Friday, not this Thursday and Friday, but next Thursday and Friday is student holidays. We've got staff meetings, faculty meetings. Faculty meeting on Thursday, and I think school, and Friday is school-wide employee meeting. So I have to go to Gordon campus all day, both days. So it's not a holiday for the faculty, it's just for the students. And then that next week I'll be in North Carolina at 2 different conferences in eastern North Carolina. According to Google, 550 miles from here. So I've got a lengthy drive on Monday and Friday, and supposed to have some seminars on Friday morning to attend, may even have to present mine day, because they haven't told me who's presenting at what time, and they told me they were going to try to put me in the morning. But they don't have anything on Friday afternoon anyway, they're right out at lunchtime. So I've got to head back here at that point. So that will be a full week. And this week, as soon as when I let y'all go, actually I'm going to go back to office, and hopefully SQL Server will have installed, and I can go through and update a set of directions for them that I told them last night I would do. It doesn't like to install on my computer at home for some reason. Although it may be, I didn't look at the computer this morning, walked out to see if it had gotten further along last night, but it's been stopping. But it is installing on the one here. So I thought I already had it installed on the different machines, but it went somewhere. In any event, chapter 5, we'll get through it today. It's not as much stuff in here as we had in the previous, but then the next chapters, there's a lot of stuff in there. And actually, next week's I've got scattered over 2 weeks. Chapter 6 is set for 2 weeks. But Thursday, I'm going to start in on chapter 6, since we'll be done 5 today. So they go through a number of things in here, but it's not quite as much as you had in the other. It's talking about Ethernet in this chapter, and Ethernet's going to be the approach you're going to use for most of your LAN networking today. It's not always been the most popular one out there, but it has been for a good long time. And Ethernet is an old protocol out there, so that it really dates back to 1973. First I dealt with Ethernet was in the late 80s. And I did token ring before that, and actually did token ring on for a number of years after that, doing more token ring than Ethernet. But the first I encountered Ethernet really was very late 80s, and it was when we wired all the schools in the state, all of us except for 2, I think it was, I know 1. Seems like there was one other school that did not go token ring but chose to go Ethernet instead. Token ring has basically died now. Token ring had a problem of it had limitations on the number of devices you could get onto it, and Ethernet, you're pretty wide open on what you can expand it to. So Ethernet gradually gained on everything else and has taken over. And there were others out there too, but the Ethernet protocol's been there. So you can send all kinds of things across what's being used for your lanes. They mention about bandwidths that it supports. That's current bandwidths that it supports that they're giving there of the 10 megabits, the 100 megabits, and so on. It did used to support slower speeds than that back in time. Although going back to the 80s, to about 1990 when I encountered it, it was running at 10 at that point. Because Token Ring had been at 4 and had gone up to 16 in the early 80s. And then it sort of bogged out at that point, and that's where Ethernet sort of left it. But Token Ring actually is still around, not as Token Ring specifically any longer, but it says FDDI, which is Fiber Distributed Data Interface, I think. It's fiber something, distributed data, I'm pretty sure it's the other part. I can't say for sure on the I, and I won't say definitely on the D's. But it is FDDI, and that's Token Ring on fiber. And you will find some hospitals using it because Token Ring is totally reliable, where Ethernet is a best effort protocol. That it makes its best effort to send things to locations, but there's no guarantee. Token Ring guarantees things are going through, which is the reason hospitals have liked using that approach. Because if you're laying there in ICU, you want the nurse to know when your heart stops beating or whatever goes wrong. You want that message to definitely get back to the nursing desk. You don't want a best effort by the machine connected to you to the machine that they're watching. So you will find sometimes FDDI used in there, and that was one of the places. But Token Ring was used all over the place in the past. It was an IBM product. But now that we're in a much broader world, Ethernet's sort of taken over. All right, so speeds there they mention. 10 megabits, you could probably find some spots out there today that still are running a LAN at 10 megabits, or at least having some devices in it at 10 megabits. In Ethernet, things are going to run at whatever the fastest speed they can run it. So if you've got several devices there that are 100 megabits and there's a 10 megabit device, then all of the hundreds are going to run their 100 except when they're communicating with the 10 megabit device. Otherwise, they'll run at 100. Now on Token Ring, it ran the opposite. Whatever was the slowest device on the network was the speed the network ran at. And I just told you they had speeds of 4 and 16, and I actually got 100 now too, although I've never used a 100 megabit Token Ring. And if you had any devices on a Token Ring network that were still a 4 megabit device, the entire network ran at 4 megabits. You had to upgrade everything to get the increased speed. But with Ethernet, you can put faster devices on your network, and those faster devices will run it faster connecting to the other faster devices. They'll run it, everything runs at the fastest speed it can run it. Does that make sense to everybody? So it's one that's easy to upgrade as you go. That when you need to replace some device, you want to go ahead and replace it with the higher speed device. Okay? And that you don't have to just go in and replace everything all at one time to get the higher speed. So you can start on a slower approach to it. 100 megabits and 1,000 megabits is what you're going to find most Ethernet running at today. So that's the speeds that most of your LANs are running at, is those two speeds on the 100 and the 1,000. In here, as far as I remember, we are running at 1,000 in this building on the campus. I can't remember for sure. I think we are on all of the buildings, but I'm not for sure on the other buildings. But this one, I know they did do the 1,000. Okay. There is 10,000 or 10 gigabit speed Ethernet. I've heard of some places doing that one. There is 40,000 megabit or 40 gigabit. That will fit into one place I already told you about that's got it, and that is SunTrust Stadium's running at 40 gigabit Ethernet through their on it. And that they are in turn, and that they are connected outward that way too. And then they mention 100 gigabit service on Ethernet. I really haven't heard anything about that anywhere. Haven't read any articles about that speed, but I do see articles about 40 as the direction to go now. And actually, a lot of things I'm reading seems to think that a lot of places are going to skip the 10 and just go straight to 40 from the 1 gigabit or 1,000 gigabit, whichever way you want to look at it. But when you buy a device today, most of your devices are going to tell you that they will run at 10, 100, and 1,000. So if you go look at networking devices, you'll notice that's the speeds that they've got listed on. Some of them are starting to drop the 10 off there now because it's not being used hardly anymore, so they really don't need to downshift to that speed. But if it doesn't have the 10 available on it and you do have a 10 device on your network, those two aren't going to be able to talk straight back and forth. There'll have to be something between them. Okay? So, but most of the devices, most of the things I'm seeing out there still are doing 10, 100, 1,000. Questions on that, on the bandwidth on them? So, because if you'd asked a few years ago, they would have told you that 10 was as fast as we were going to be able to get, and then they got the 40, and now obviously they apparently got 100. Like I say, I really do not remember reading anything about 100 out there yet. Ethernet is going to fall into the bottom two layers of your OSI model. Ethernet uses two different IEEE standards, 802.2 and 802.3. And the 802.2 actually falls on the LLC sublayer of the data link layer. And speaking of which, back there on the first page of the chapter where it's got the objectives, the very first objective has an error. Because it says that you're going to learn about the sublayers of Ethernet. That should be the sublayers of the data link layer. Okay? So those will fall there. The 802.3 is the number you really need to remember out of the two. Because I really haven't encountered out there being asked on tests or certifications really on the 802.2. It's usually 802.3 is the one they ask you about of which standards associated with Ethernet. Now, having said that, still be aware of the 802.2 because I don't know what the questions are on your test. And with me having said that, probably be a question on the test that asks you which standards associated with Ethernet and 802.2 will be the answer. Okay? But my experience has been that 802.3 is the one everybody always associates with Ethernet. The 2, because the 2 is only dealing with the higher level right there in the software side of Ethernet, and really only the biggest thing it's involved with is the device drivers for your NICs and such. And so the real concern on people with that has gotten less over time, because your device drivers now are normally included with the operating system. But Windows includes all of its device drivers. Just about all the device drivers you need are built into Windows 10 or in Windows 7 or Windows 8. And that you don't have to have separate drivers to install them. And that you're not having to go, you either get a CD that comes with the device like you used to, and that's what came on there was primarily the device drivers that allowed the device to talk to your processor, okay, so that it would know how to talk to it. That's all the driver does, it's the linkage there. So that's what's happening there on the LLC as far as the networking to get the network devices to talk back to the processor. And so that's all that's really involved in the 802.2. The 802.3 is where we're really getting it all configured and put out onto your network. Okay? And then they mentioned briefly about the frame, which I'm not sure why they spend much time really at all there on that part, because they're going to talk a whole bunch about it later in the chapter. And they're going to go into details of exactly what goes in the Ethernet frame. And then they mention about that besides the frame itself, there are some other terms you will see associated with the frame. And so they mentioned there about that there are fragments, runts, and jumbo frames. Fragments and runts, R-U-N-T, are the same thing, just different terms on it, and that you will see both terms used out there on different programs that are analyzing your traffic. Because some of them will tell you that you've got so many runts occurring out there that it has detected, and some of them will tell you you've got so many fragments. But all the fragments and runts is where frames have run into frames and got broken up because they ran into each other. You had a collision, which is the correct term. And when a collision occurs, what most often happens is you get lots of smaller pieces of frames floating around out there. And those are runts or fragments. Okay? That is how, where I've mentioned before about when a collision occurs, how a collision is detected, is that when your network devices see these fragments and runts, they know that there's been a collision, and that's when they'll put out the message and say, whoa, stop everything, there's been a collision, we've got to clean up and resend everything that hasn't been received. Now, the other thing that can occur in the collision, but it's less likely to occur, is you can end up with the giant ones or the jumbo frames. And that's where, when the collision occurred, that two frames ended up jammed together into one frame. And again, think in real life to like cars running into each other. Usually when they run into each other, you get lots of loose parts scattered everywhere, right? But sometimes the two vehicles end up jammed together and you got a bigger thing sitting there than you had before. Because when I got run into a few years ago in Elberton, Georgia, when I was teaching there, and a car ran into the back of my truck. It took us a little bit of work right there to get that car from under my truck. It was attached under my truck, and they were going to tow my truck in, and one of the policemen and me are going, no, we don't think so. We just got to get my truck to break loose of that car and pull off of it. And it did, and the only thing that was done to my truck was basically the bumper got bent under. And there was a couple of little tiny dents right there back by the edge of the body. All he had to do was replace the bumper. The other car was towed. That went under there. I was sitting stopped at the red light, and they plowed into me. The guy didn't see the traffic light or the stop traffic. And I realized it, seeing him in the mirror, that he wasn't going to stop when he was still a distance away from me. But that's the way it happened. So we ended up there for a little bit, that we had that jumbo vehicle, because his and my vehicles were attached at that point. Well, the same thing can happen to frames, okay? But you're not going to have very many of that, just like you don't when we collide vehicles together. This doesn't happen often, but you all have seen where that's happened, okay? That they just stuck together when they ran into each other. So those are all out there. The baby giant frames, which they didn't put in blue, I've not seen that term used before, and obviously they hadn't seen it much either because they didn't highlight it, real highlight it. So then, and your data in the frame is going to be limited to the 1,500 characters. So we're going to see that number come back up at us again. They then go through and tell you about all of the fields in the Ethernet frame at that point and describe that out to you. And that the frame can be up to 1,518 bytes long. It's going to be a minimum of 64 bytes long, okay? And the 64 is going to come back in a little bit for you to see again on it. So when you're looking at that frame, the first part of it, the first 7 bytes, actually the first 8 bytes is going to make up a preamble. It's got a byte that is the start of frame, and then it's got some basic information that it's going to include in there that tells the two devices, the receiving device, about how it's being sent, and it's going to tell it how this thing is coming across. And if it's clocking it, which a lot of times it does, and so it's sending it at a steady pace that sends each of the bits at a certain point in time, rapid in time, or what, and for how it's going to know to recognize the rest of this frame. So there's a marker to mark the beginning of it and to say, and here's how to know how the rest of it's coming in. That's basically what preamble does. Then's going to be your destination MAC address. And by it being there at the beginning, it's going to give us a way where we can speed things up slightly because it's on the front end of the frame where it's going to. Now it's the MAC address. MAC addresses are the addresses that are burned into every network device. I mentioned them before to y'all. And so then they go a little bit more detail on them here in this chapter. So the MAC address is 12 hexadecimal characters long. And it actually splits in two. Okay? It's got a unique organizational identifier on the first part, which really is just the organization. And then it's got basically a serial number on the last part. The organization ID is issued out by IEEE to all organizations that make network devices. They give them a number, and they always use that number for the first part. The last part of it, the organization creates and assigns themselves. Because what you want is every networking device in the world that connects to a network has a unique MAC address on it. So no two devices have the same address, okay? But it doesn't tell you anything about where it's located. The IP addresses that we're going to get into the next chapters tells you where is it located. So everybody follow on that? The MAC address just tells us that this is gives us a unique address to it located somewhere in the world, okay? It will tell us who made it. And you can actually go out to the WCC website, type in a MAC address, and it'll tell you who was the maker of that device. Because that first half, those first 6 hexadecimal characters, gives you that information. This is also 48 bits long. Okay? Then, there's that. Now, they are actually, at this point in time now, starting to reuse some old MAC addresses. But equipment that was made in the early 80s and in the 70s, is it in use still out there on networks? No, because it's extremely slow and would never work on our stuff today. So they can reuse those addresses and not worry about that there's going to be a collision of 2 of the same address on the network, okay? The only organization address I can tell you out there is I know Cisco's, and it's 00000C. I don't know what anybody else's was, and that's not even the one Cisco's using now, but that was one that Cisco was given initially, okay? It makes sense. That's an easy one to remember. It made sense for them. I have no idea what Juniper, Netgear, what the current Cisco ones are, or anything else of what that part of the address looks like. But that one.
So, like, does a virtual machine have a MAC address?
Yes. If it's going to have a MAC address, but it's going to create its own MAC address on there from that. But it's really using the MAC address of the physical device. When it goes to the network, remember, it's got to pass through your actual physical network device, so that's the MAC address that's seen out there in the world. But it is going to assign a MAC address to internally. That one, though, could be a duplicate somewhere else in the world, but it just makes that one up. Okay? But it doesn't make any difference because nobody else ever sees that address. Because that's just purely internal. We'll see on IP addresses that you're going to have addresses that are purely internal also. Now, the other part is the MAC address does play a second part, though, in terms of logical addresses today. IP version 6 addresses, and there's 2 different ways to create the numbering for them. One of the ways that it creates the numbering for them will use the MAC address as part of the IP version 6 address. Okay? So prior to that, of when they put that in, and if I'm remembering right, they use a Slack to do it. That they were 2 different things, but now they actually do have some mixture together. All right. The other part on the MAC addresses is the chapter goes ahead and introduces to you hexadecimal. Really doesn't belong until the next chapter to me. Okay? And they show you a table with hex and binary. They really don't tell you anything about the binary. And don't hardly tell you anything about hex. And then they tell you down there if you're going to convert numbers, best thing to do is convert it from, if you're going to go to hex, their suggestion is go through binary to do it. Okay? When we get into the next chapter, and it may be Thursday or Tuesday, I'll go over this. I'm going to go through the number systems. But since they throw it there to you slightly, I'm going to go ahead and tell you briefly about what hexadecimal is. And I got to give you a tiny bit of the lecture I'll give you on number systems. Okay? So I don't like it sitting right here, but it's here, so that's the way it is. The number system you all use is decimal, which is a base 10 number system. It has 10 single-digit numbers in it. Why is it that humans, as a generality, have used decimal? Why would we have adopted a base 10 number system that has 10 single-digit numbers?
Our fingers.
Your fingers. Okay? Now, it's not the only one, and when I talk about it later, I'm going to go into a little bit more on that for you, okay? There are other number systems that humans have used, and there's reasons why they used them, okay? But we've adopted onto 10 at this point, okay? Computers, so humans are going to use decimal, which is going to have 0 through 9 in it. Computers don't work really real well as far as internally in them, in terms of decimal. Because how does a computer work? What's it working off of?
Binary. Binary.
Well, it's going to use the binary number system, but the question is, why is it using binary? Why would we have chosen to have computers use binary instead of decimal or whatever? Because when you type something into your keyboard right there, it converts it to binary and works with it. Okay? It's going to store it using binary. And when it puts it back out to you, it does a conversion at that point and displays it to you back in decimal. So you can switch stuff between all the different number systems. There's an unlimited number of number systems.
Is it because it imitates switches? Is it because it imitates switches? Like on and off?
Okay, so it uses switches, but what's it using? What's it using in those switches? Why would you be big on using switches in there? How does the computer run? This isn't in the book on you. You're not going to find the answer there. How does it run? What's it run on?
Processor?
Hmm?
The processor?
Let's get more basic.
Electricity, so like on and off.
On what?
Electricity.
Electricity. Now, if you got electricity there,
Get positive.
or when you're looking at your disk, you're looking at magnetic stuff, or when you're looking at your CD or DVD, you're burning holes or not burning holes. Think about what all those things we just said as far as the easiest way to express them. It's either there or it's not there. On the CD, DVD, there's either a hole there in the DVD, CD, or there's not a hole there. Okay? Electricity. On-off switch to turn the lights on and off. We could put a variable switch up there, but then if I sent two of you up there to turn on the variable switches and tell you to turn it on till the lights are on 70%, are y'all going to get it exactly the same? No. Okay? But I send you up there to turn the lights on or turn them off, we'll get exactly the same on that, right? So expressing it as ones and zeros makes it precise on it, okay? Instead of, if we tried to do the other, it gets variable on it, and it gets sloppy. And how do you put part of a magnetic charge onto the disk and figure out you've only got part of it or whatever? You want it either there or not there, and if it finds something of it there, it thinks it's there, okay? And just like where we looked at where crosstalk and interference can mess with your signals in the last chapter, as long as it sees it a certain amount there, it assumes there really was a signal there. That makes sense? And so the 1 and the 0 works well. So it uses binary. So we put computers using binary for that reason. They only have zeros and ones. Okay? But now we got a problem. If you go in and you look to see exactly what's stored inside the machine, and you can do that in several ways, or to see what's exactly coming across the wire, it's a whole bunch of zeros and ones. What's going to happen when y'all look at a whole page of all zeros and ones and you need to find the 300th character on that page? Probably going to go crazy looking at it, right? You're going to start seeing zeros and ones bouncing all over the place on you when that's the only thing you're looking on there. So it's sort of like where you look on Facebook and people send out the things for you to find the 7 in that whole little chart there, or to find the 8 and everything else is zeros on the chart. It sort of goes crazy on you at that point, because that's exactly the same thing you're looking at if you look at a pure dump of memory or of what's coming across the wire. Okay? Well, to convert it back to decimal doesn't convert. It will convert, but it doesn't give it to you in the raw type approach. And you may be wanting to look at it more of exactly what was sent across, back down to the zeros and ones, but don't go crazy. Hex gives us that ability. Because with hex, so hex is not going to be used as what the machine actually is working in. It's not going to be what we're working in. It's just an easy way for us to see what's in the actual machine. Okay? Because with hex, it's a base 16 number system. This is a base 2, this is a base 10. And that's how many digits are in the number system. With hex, you can take 4 binary digits and express it as a single hexadecimal digit. Okay? It's not going to work like that of binary to decimal. Okay? But you'll get exactly the same thing out of it. Does everybody follow what I'm saying? But it's going to be very clean, and what it does is gives you a shorthand way of seeing the binary. Okay? So things are going to, instead of going through all kinds of conversion on it, you can take 4 binary digits and make them into a single hex digit. So when we're looking at these MAC addresses, instead of looking at addresses that are 48 bits long, we can cut it down to 12 bits, not 12 bits, but 12 characters, which actually is less than that, which is actually 6 bytes. Okay? We can convert it down to that and see what's there, but express it much simpler where we can read it better. Instead of when we look at it and seeing 48 binary bits, and I ask you, what's the MAC address on that DIC? And you start reading all zeros and ones to me. We're going to get confused, right? If it's 12 hex characters, we won't get that confusion on it. Okay? Now, it's got 16 single-digit numbers in it. So it's going to express it, and each 4 bits will express as 1 hex character. So that means 2 hex characters will represent 1 byte, from what you've heard before. Okay? But a byte is 8 bits long, so that means we can express 1 byte into 2 hex characters. It's going to consist of 0 through 9. That's the first 10 single-digit numbers in hex. And then any number system that has more than 10 single-digit numbers in it, you go to using letters for numbers. So what they told you in first grade about what was letters and what's numbers doesn't hold now. Okay? So we're going to use A through F as numbers in it. And just for your information, if you go to a number system that's higher than base 36, it goes to using Greek letters as your next numbers. Okay? Beyond that, I don't know. And I'm finishing reading a book on numbers, history of numbers. But here we're going to use the letters A through F. And think about it, when you looked at MAC addresses and you looked at some other things on the computer, you've seen that, where they told you it was some number, but they told you, but it had numbers and it had these letters in it. Those were numbers. Okay? So your MAC addresses are going to be expressed in all of this. Does that make sense? I'll get the basic idea there. Now, we're not worried about how to convert them or anything else right here. Because the book doesn't tell you any of that in this chapter. But they did throw you the chart of all of those. So you can look there and see on it. But we'll talk about that probably on Thursday or Tuesday. Okay? Because you're going to need to be able to do that to be able to do some stuff subnetting when you get into IP addresses. But just be aware of the 3 number systems. There is a 4th number system that you will see sometimes used out there, but really not anymore, that mainframes used to use. And there are some machines that still do use on it, of some bigger machines. And that's octal, which is a base 8 number system. But that was very rarely used. I really haven't ever used that. Everything I ever dealt with was always hex and binary and then decimal. Okay, but you may have somebody tell you, well, octal's used out there too. Yeah, it is, but it's very rarely used. And it's a base 8 number system. So I don't teach octal because I've never used it. All right, so you got a destination MAC address and then you got a source MAC address. Destination MAC address is what's the next device it's going to, not the ultimate destination unless it's down to that point, okay? Unless it's gotten to the right network. And destination MAC just gets us to the next point. Source MAC address just tells us where did it last come from. So at this point, which device just sent it, okay? Doesn't tell us where it originally began, doesn't tell us where it ultimately ended, unless we're at the very beginning or the very end. Or if it's right there on the same network, and then it would have actually the same thing. Okay? The IP addresses are going to tell us the endpoints. MAC address is going to be, as we're working our way through, where to come from, where to go to, where to come from, where to go to. It mentions source MAC addresses have to be a unicast address. It has to come from a single device. Destination can be going to a single device, or it can be sending it to a number of devices in a multicast address, which it uses an address that then tells it actually goes to a number of other addresses than just that one address. Or it could be a broadcast address where it's an address sitting there that says, send it to everything. Now, broadcast addresses are going to be the highest address number you can have in that network. And in hexadecimal, that's going to be normally F's as your character, because F is the highest number we can have. Okay? When we look at IP addresses, the highest number is going to be 255, but you'll see the reason on that. The 255 is the biggest possible number, because it's looking at a byte on it. And that comes back to where we've gotten all this trying to transfer across. Then it's going to have a field there that it says is the ether type field. What that's going to tell you is which version of IP is this frame that it's going across. The stuff that's in it, is it using IP version 4 or is it using IP version 6? Okay? And at some point, probably everybody prediction at this point, long in the future, they'll have to make an adaptation on that to tell it to be able to tell it when it's IP version 7. But they haven't even started thinking about that because everybody's saying IP version 6 is going to last forever. And I've already told y'all that's not true. I know it's not going to hold up. Then comes our data, And that's going to be where it's got the packet that it's encapsulated. And that's going to vary in size from 46 bytes to 1,500 bytes long. Okay? The 1,500 is the number you really want to remember off that one. And then the last thing it has is a frame check sequence, or FCS. It has a number on the end of the frame. What that is that's to check to make sure the entire frame arrived undamaged. It's a reliability check. It's not a validity check, it's just a reliability check. When it goes to make the frame, the last thing it does after it puts all that front end information on, it runs a calculation on that frame. It uses a special algorithm to do it and comes up with a number that represents that frame. Basically, it goes through and adds all the on bits and has a number off of that. Okay? And puts that number on there. And it may drop off of several of them. It's only got 4 positions, I believe, for the number. Okay? So, but it comes up with a number from it. At the other end, when it's received, the receiving device gets the first part of it, does calculation, same calculation as the sending did, and compares the number it came up with what the number is on the frame. If the two numbers match, we can reliably say we've received the whole frame. Now, it is possible that the frame got damaged in such a way that the same number got calculated, but very, very unlikely. But it could happen. Okay, so that's why I'm saying it's reliable. Doesn't do anything about whether what's in there is what's supposed to be in there. It's just making sure what was supposed to have been sent is what should have been received. Does everybody follow on that? Any of you, and she would still see this, with dial-up, that when the frames coming to your dial-up get messed up, you'll see on your little indicator down there that it'll start flashing little red lights on it, telling you that it's dropping stuff on it. It's doing that through the FCS. It's saying, wait a minute, stuff's not making it, or it's getting damaged, or taking too long to get to me, or whatever. There's damage occurring to the frames in the process, and that you've got a messed up connection. You got to, usually when you start seeing a bunch of the little red lights sitting there, you had to hang up and reconnect again. And then a lot of times it then got a circuitry true to your ISP that was good, and you didn't pick up all of that. You could have been picking up bad traffic along the way that interfered. Does everybody make sense off that? So that's what the FCS does. All right, then they go through and they talk about the MAC address, about the addresses, and talk about the hex there, which I just talked about to you already, and gave you all of that information. And then they talk about how the MAC address is designed. I already talked about that. I told you I'm not going to always follow in order in it, but if we're going to tell you there's a MAC address there and it looks like this, I probably ought to tell you what you're really looking at there, because otherwise it looks confusing to you. And so that's why I keep jumping around on it. And so they go through and describe that one to you, and they actually give you another number for Cisco there that Cisco's obviously at some point in time has been using, apparently currently using 00602F. Okay? It's not anything you got to remember. You don't need to remember the 00000C or that number that's in the book. That's superfluous information for you. It's just an example for you. It's not something you ever need to know, okay? If you need to know who manufactured the device, FCC's got a wonderful little thing on their site for you to type it into, and it throws it back at you and gives you the identifier. Okay? Except for when the government was shut down, that one wasn't available there, but the other people have got the same thing sitting out there, so there were other sites you could have gone to during the shutdown. But it was not available on the government's, on the FCC site during that time period. But normally it's always there. So then they go through and they start leading you through about what happens, because it looks at that MAC address, compares it, it's going to use ARP then, and this is the rest of the chapter basically in summary, and they go through a number of pages walking you through all of this. It's going to use MAC addresses, and this layer 2 is going to use the ARP protocol, ARP, Address Resolution Protocol. ARP is a lot like DNS, except working a different level on it. DNS is one that you all are probably aware that you use and that you've seen sometimes when it messes up, you've got problems with your internet connection. Because you can take down your DNS server and effectively, for most people, they have no internet connectivity and they're convinced their internet's down, but they've really still got connectivity to the internet, they just can't use domain names. Okay? DNS will take your domain name and convert it to an IP address, which is what we're doing in the next chapters. Okay? So that takes dwightwatt.com and says dwightwatt.com is located at IP address 68.75.42.3 or something. I'm not sure what the real number is. I've seen it, I can go out and look it up, but I don't know it. Okay? And then that's where, if you were typing in www.dwightwatt.com, that's where to go make the request to get the page sent back to you. Does everybody follow on that? The problem is, it's really not going to use the IP addresses it goes across the network. It's going to use MAC addresses as it goes, but the IP address is going to tell us where we're ultimately going. Okay? Because that's the logical address. To get the MAC address of that device, or the devices to get there, it's going to use ARP, Address Resolution Protocol. ARP converts IP addresses to MAC addresses, or vice versa, and you can actually do vice versa on the DNS also. Take an IP address and find out a domain name or domain names associated with the IP address. Okay? So it's going to go, we go to send it, the IP, it's got the IP address, so then it uses ARP to get the MAC address. Now, when it uses ARP, it's not going to go out and do a broadcast right off. It's going to look in the MAC address table or the ARP table. You'll see it labeled both ways. And that's going to tell you, have in there what it currently knows as MAC addresses associated with IP addresses. If it knows it, it goes ahead and uses that address. Now, it only keeps the addresses in that table for a certain amount of time and drops them if they haven't been used again, so it keeps it as a current one on it, okay? If it doesn't know what the MAC address is for the IP address we've got, it's going to send out a broadcast and say, does anybody know what the MAC address is for this IP address? If nobody responds back, it's going to use its default gateway and send it and put that in as the MAC address for that IP address and send it to there. That device will in turn look at it again and go, okay, do I know what the MAC address is for this IP address? If I don't, broadcast and see if anybody does. And if nobody does, send it out to the default gateway again. And it keeps doing that all the way along. Now, each time along the way that it comes to that, so it's going up and down our OSI model, it keeps putting the MAC address for the current machine on there as the source, and it's putting whatever MAC address it comes up with at that point as the destination. And that's where it's to go to next, and then find out more information. Does everybody follow on that? So it's going. There's a table kept there on your devices. That's a MAC address table, or you will see it as an ARP table. And I don't remember which way it refers to it in the book, but you'll see referred both ways. That keeps track of ones it currently knows. Same thing's happening on DNS. And it's actually why sometimes that you're going, somebody else may tell you the internet's down, but you can still get onto pages that you've already been to. But you try to go to a new page and it won't let you go there. Because if the DNS server's down, if it's a page you haven't been to recently, it won't know about it. But if it's a page you've been to recently, if the DNS server's down, you can still go there because your machine knows what's the IP address for that domain name you're putting in there. Does everybody follow on that? Same thing's happening down here on the MAC addresses. So you still could have connectivity out there, but if all the parts aren't working right, you may or may not have the connectivity you want. Okay? And that your ISP's DNS server may go down, and that if you go in there and just change what DNS server it uses, you may be able to keep right on working. And Google actually maintains a couple of DNS servers that a lot of people will go to for in those cases, or use as an alternative, or some will use it as their primary, that are addressed as 4.4.4.4 and 8.8.8.8. And they are large DNS servers sitting out there in California. At least that's where I think they're sitting. Because Google's had them from back in the beginning of Google. They put those out there as services. They needed them for themselves, and they opened them up to everybody else to use also. And we use Google for all kinds of other stuff, so lots of people will use those. But Comcast has got their own DNS servers in different locations. Charter's got theirs on, and so on. Everybody that's an ISP has a DNS server. We got a DNS server sitting here in the school, and then they go on up in levels, we'll find out too. All right, so if you want to find out what your MAC address is for a device, ipconfig or ifconfig will find that for you. ipconfig on Windows, ifconfig on Linux, Unix. And it should be on the Mac also because it's a Unix derivative. Okay? To keep Bill Gates and Paul Allen out of trouble, it's ipconfig on DOS Windows, not ifconfig, because DOS was really a copy off of Unix also, but they changed a few things to make it different. Like slashes to backslashes, and ifconfig to ipconfig. So if you do an ipconfig/all, it will tell you what the MAC address for each of your connections are. And if you were on the virtual machine and you did that, it would actually should give you the MAC address that it has come up with for its virtual internet network connection, and give you actually the MAC address for the real network connection that it passes through. But I'm not real sure it always does give you both numbers on it. But at that point, you're really only concerned with the MAC address back inside. But it's got to go through the outer machine, so it uses the outer machine. All right. I talked about unicast, broadcast, and multicast already on that. Multicast is the one you're not going to see used as much, but that's saying send it to a select number of machines, but it puts one address in there that it then uses as a holder separately that keeps track of the addresses it's going to a group of addresses. Broadcast says send it to everybody. So everybody that's on your collision domain will get that message. Okay? Now once it crosses a switch or it crosses a bridge, that goes to another domain, a collision domain on it, and it does not cross that point of broadcast. Okay? But if you had a hub in there, everything in there will cross through a hub, because a hub does no checking of stuff. It just transfers it all to everywhere, which is one of the ways that hub switches are much faster than hubs. I really already told you about how it learns MAC addresses, how it forwards the stuff. That I didn't tell you. Let me see where in the world we are on pages. And they got lots of illustrations showing you where it's going through the switches and going out certain ports and how that's done. So the switch forwarding method, so I'm over on page 240 now. But most of y'all seem to be following on books. Or if you're online, it's 5.2.2. That's this and one other thing is really all we got left in the chapter. Switch forwarding is when it comes into the switch, how does it descend it on out of the switch? Okay? On the previous pages, it talks about what we just talked about, that it's going to look at it and figure out which port does it send it out, and it's only going to send it out on the port it belongs on. Does it make sense to you on the switch? Hub, it just travels straight on through. Hub's just a thing that lets you wire them all together, but doesn't do anything to it. But the switch is going to look at it as it comes in. When it comes in, it's going to look at it and send it only out the port that it really belongs on. It's not going to send it out all the other ports. You ready to follow on that? Now, when it comes in, there is a couple of methods that it can use to forward stuff. And when y'all get into more advanced Cisco classes, y'all will actually set this stuff up. You're not setting it up in this course, okay? You're just learning about it. There is store and forward, and there's cut through. Okay? Store and forward says when the frame comes in, we're going to get the whole frame in and then look at that frame and then decide where it goes. Which is probably what you thinking from what I had just told you was going to be doing. You were thinking in your mind of how it would do it. It gets the whole frame, it does the FCS calculation, looks at the destination address, and then changes those addresses and sends it out. Y'all follow on that? Now notice there, it came in, and I just talked to a number of things it did right there and sent it out. So there's a delay in that. Does everybody follow on that? But remember where the destination address is. That was on the front of the frame, right? It came right after those first 8 bytes. It was in the next 6 bytes following that preamble and start byte. Okay? There's 1,500 and some bytes sitting behind it, right? Still coming. If it was a train, we're going to get to where you've got choices of which ways it's going to go. And the train's going to come to a stop and then figure out where to go, switch the track correct, and then go. That takes time, right? If we do cut through, what cut through does is cut through gets those first 64 bytes. Well, actually it gets less than that, depending on which way it's doing it. It gets as far as the destination address, gets the destination address, does a calculation on that one, looks it up and sees, all right, where's it belong? And all it has to do is change those 2 addresses on there on the front. Remember, so it gets the destination and gets the source, and it changes the source to itself. Sets the correct destination on there and keeps on sending while it's still coming in. So the frame is still arriving and it starts sending it on out the correct port. Y'all see on that? Instead of the whole thing comes in, does stuff, and then sends out. Now the very first part comes in, the other is still coming in behind it, but it goes ahead and calculates on this and ships on out. Okay? Faster on its sending it. However, there are some limitations. If it is a runt or a giant, it doesn't know that. Unless it's really a real runt. Okay? That it's missing that first part. As long as it's got the first 64 bytes, it knows it. It says it's good. But the rest of it may be all damaged behind there. Does that make sense? And it will send it on out. So it will forward bad things. Okay? So if you've got lots of runts occurring, lots of collisions occurring on your network, causing lots of runts and giants floating around out there. Cut through will give you problems. We'll end up putting a lot more traffic sitting on your network than you need to get there. Store and forward would get rid of all of those things. Okay, because it would drop them because, whoa, SCS didn't work. Okay? And it just drops the frame. But if you've got good frames as a general rule on your network, it speeds it up for you. Because it's not having to stop and wait. Okay? It's a whole row of traffic, we're all traveling together, and the light turns red on the first car. Does it have to wait till all the other cars get there to the traffic light before it goes? Might have to sit through a couple of red lights, depending on how many of us are involved, right? Or if any of you have ridden in a real large funeral, or sat there and watched a real large funeral go by. Of how many lights do they go through when they get to run the red light? Okay? Because they're doing cut through. We're normally having to do store and forward at the traffic light, right? But they get the amenities of playing with the blue light that day. So store and forward, the whole thing comes in, it checks it. Cut through, it sits there and just looks at the first part, and as long as that's good, they can recognize the addresses on there, it starts shipping it on out. But it did not do a check on the whole thing, so it did not check the FCS, so bad ones can be sent. So generally, though, you do want to use cut through on it. Now, cut through does have two choices on it, a fast forward, which is really more of what we were talking about right there, okay? And then there's fragment free. Fragment free says if we just use plain cut through, it just looks as far as that source address and starts making a decision off of it. Because it's got to put the new address onto it to ship it on out, so it's got to get that far on it. It's got to change the source to its own address, okay? And it's got to change the destination to where it goes. So that's all it needs is those 12 and 8, the first 20 bytes, okay? Fragment free says we're going to look at the first 64 bytes, which gets us back into the data and to the minimal size of data. Because remember, the size of the data we say could be 48 to 1500 bytes long. That will take care of the minimum size of a frame and make sure that there is to that point that much. So that will drop off a lot of our fragments at that point. That will kill the small fragments that are floating around. Bigger fragments that are floating around still will go through. Jumbo frames will still go through, but we've cut out some of the bad stuff from being forwarded. Okay? We've put spam filter on it. To use another look at similar type thing. Okay? Does everybody follow on the difference there? Now, so that's your different forwarding methods. Be aware of the two major, and then say cut through actually has a special cut through, a general cut through, and then has fragment free on it. But you're generally just going to see store and forward and fragment and cut through. That you're going to just see mentioned normally just store and forward and cut through. Although cut through can have its own little specialized one under it. The last thing in the chapter, and this is down to the last page of the chapter, is that they mention to you about some problems with ARP on this stuff. And that you've got ARP spoofing, and then the ARP broadcast. And I've actually already mentioned the ARP broadcast to you. When it sends out a broadcast, that puts a large amount of traffic on your network, okay? Because it's sending it to everybody on that network. So if you want to keep those down, that you don't want, you really want it to build stuff in the tables and hold stuff in the table as long as logical. You don't want it to hold it forever, although you can put static entries in ARP tables. if you know this is the address for it, you can build it in there instead of it having to go out and try to find it, which is the way it used to be. But that doesn't give much play in it, so you sometimes will see static entries put in them, but most of the stuff is dynamic, and it replaces it over time. And most things people are doing the same things on networks. So most of the time, it really doesn't have to be broadcast. So the broadcasts really don't get into being a big problem. They're set initially when machines come on. Okay? So for the first initial part, they got to build the ARP table again, and then they're set to go. The other one is ARP spoofing. And that's a way to mess up a network. You can go in there and fake the MAC address on it. And you can go in and doing the spoofing, change what the address it's sending stuff to on the gateway, and change the gateway address. You can get into networks and do that if it's not protected on. And people will do that and change the gateway so that or we'll go in and tell when somebody sends out our broadcast saying, what's the MAC address? Instead of replying with, here's the gateway, or what the address should be, it'll send back the reply for its machine going out instead of what should be, and then it can steal the traffic and read the traffic. So your word's gone out of my mouth now. But your malware agents, and malware is not the word I want there, but your bad agents, okay, will use that as sometimes a way to steal traffic and find ways into a network thing. Because if they can get into that, then they can get real addresses from within the network to be able to know what MAC addresses to attack to. So the ARP spoofing is just another way to be able to attack a network. And you can build defenses to stop that. Your firewalls will block that out on you if you set it up correctly, if it is an active firewall. Now your Windows firewall won't, because it's not an active firewall. But your IPSs will. Your IDSs won't. Although your IDS will quite often see it has occurred, but it doesn't do anything about it. Questions? Because that's chapter 5. And they go through a lot of illustration on the process to you on it, okay? And there's not a reason for us to sit there and talk all through all those little illustrations. So I really led you through the basic idea of the illustrations anyway. And it's y'all's job to still read the chapter anyway. I'm just going over the big things on it and then giving you some extra information on some stuff and then describing it more some and then skipping over things that aren't quite as much on it. Because when textbooks are written, the idea of it, if you write the books right, you really give 125% of what the material you think should be taught in that course. Because different instructors think different things are more important. And if you do that way, you get everybody covered on covering what all they want. Now I say, they spent a couple of pages right there just telling you about what those number systems were, but they really don't go into what's on it. So I'm not sure why they even show you the binary chart there, because they don't tell you anything about binary there, other than to intimidate people. So at least now you know it's a base 2 number system and it only has zeros and ones. But there's unlimited number of number systems out there. And we'll talk about at least one more, but we won't go into it. But I'm going to tell you about one more. So I'm going to give you a little bit more history on numbers. And then we'll go through and do conversions. And I'll teach you how to convert from one to another. so that when you've got a decimal number, you'll be able to put it in binary or put it in hex, and any direction around on that. Okay? And I'm going to show you my system on it, which really goes back to what my Cisco instructors taught me pretty much of how his was. That makes the most sense to me. It doesn't follow, it accomplishes the same thing as what they show you in the book, but is a little bit different. I think, I really haven't looked at the way they're doing it in this book. It's different than what some of them in some books. There's some different ways you can go about doing it. There's one way that a lot of the books want to use that I can't, it doesn't make sense to me yet how to do part of it, but where my system does. If their system makes sense to you, use their system. Okay? I'm not going to tell you my system's the way to do it. Whatever way, there's more than one way to do some things. And whichever way works best for you is the way to do it. Now, the other thing I will tell you is that yes, your computer, your phone, your calculator, if you've got a more expensive calculator, will do those conversions for you. If you've got a scientific calculator, it will convert numbers from one system to the other system for you. Okay, likewise, you can find plenty of apps and programs out there on the internet that will do the same thing. So you can put an app on your phone. The only thing is that doesn't do you any good for your test, doesn't do you any good for a certification. But if you're out working, yes, you can look things up. But if you know how it's done, and you don't always have to do it using what you know, but if you know how it really works, you can see how it really works together. Okay? And what's going on there to make sense of what you're looking at. If you don't know how it's done, you're going to get confused on some other things we're going to look at. Because when we look at subnetting, which yes, you can get it to do out there on some generators, but you can do a much better job, and your questions are always going to throw you some strange different thing off of it. I just set up the test for Skills USA. Well, I'm in the process of finishing setting it up, and one of the things we're doing at Skills USA state competition, which we've copied off the national competition, is they have to be able to do that type of stuff. Convert and divide up networks, which is what we're going to look at next. And if y'all get that part, you've really got a major part of this course done right there. If you understand the models, and you understand how to do subnetting, you can just about get through the rest of this and the next class. And really, the third and fourth class, but I already told you, third and fourth class gets easy, it's built on everything else. It's sort of like if any of you have taken accounting, learning the equation in there and knowing what the difference between a debit and credit is. If you can get those two things down in accounting, you got accounting licked. Once I figured those two things out, I made it through 5 courses of accounting without problem. It killed me in the first course until I got those two concepts learned. What were debits and credits? And what was the basic formula there of assets equals liabilities plus equity? Right, any questions? Then if not, I kept y'all late, I think, the other day. I'll let y'all go 20 minutes early today. Unless y'all want to protest that. Then I can come up with something else to talk to you about for 20 more minutes. But if you get me started now on something else for 20 more minutes, it's going to take me 40 minutes to tell you all about it.
I got DSL now.
Oh, do you?
Yeah, a whole 1.5 download and a 0.5 upload.
Only 1.5? They didn't get you to 6? They should get you to 6 pretty quickly then, because 6 is usually what DSL works off of.
They said I'm on the end of the line.
Yeah.
Get the line of telephone, so they can get me the